Welcome to Geometry, Lesson 12.1a. We're learning about trigonometric ratios. The foundation of trigonometry is the many ratios associated with right triangles. Trig actually came from the science of astronomy and the necessity to measure distance between stars. Chapter 12 explores three common trig ratios. We have sine, cosine, and tangent. The AA similarity postulate guarantees that any two right triangles having a corresponding pair of congruent acute angles are similar triangles. So we'll be using the AA similarity postulate to help solve our triangles when we're using our sine, cosine, and our tangent. Let's take a look at these two triangles. We have smaller triangle ABC and triangle XYZ. They both have congruent 90-degree triangles, and they have congruent acute angles A and X. Because they have two pairs of angles that are congruent, we can use the AA similarity postulate to state that the two triangles, triangle ABC and XYZ, are similar. And we can also state these ratios and proportions. And we have XY, which is a hypotenuse, which corresponds to AB, another hypotenuse. We have YZ, the short leg, corresponding to BC, another short leg. And we have XZ, the long leg, corresponding to AC, the short leg. So similar triangles have corresponding parts, and we know they're similar because of the two congruent angles. Cross products of the first proportion from the last slide, XY over AB, which was the hypotenuse in both of these triangles, show that if we multiply XY times BC, it will equal AB times YZ. So let me say that again. If we multiply XY times BC, this is the hypotenuse of the large triangle, multiplied by the short leg of the small triangle, that we can do the same with the short triangle's hypotenuse and the large triangle's short leg. So they will be equal to each other. And we know this about similar triangles and their similar parts, that we can create many different proportions. Dividing both sides of the equation above by AB times XY results in the following two proportions. And we end up with BC is to AB, so the short leg is to the hypotenuse, as YZ is to XY, also a short leg to the hypotenuse. So we have created another set of proportions between the two triangles, and this is just showing you how to derive these proportions from the original proportion that we started with. If the same reason is used for the other two proportions, the result is that any two sides of triangle ABC is equal to the ratio of the corresponding sides in any similar triangle with an angle congruent to angle A. So taking those same two triangles and adding values, we can now set up a set of proportions between them and have them be equal. So let's start with the small triangle, and if we take BC to AB, which was one of our proportions, that's 6 over 10, and that equals YZ to XY, which is 9 over 15, and they both reduce to 6/10 or 3/5. If we take the long leg AC to the hypotenuse in both triangles, we'll have 8/10 equals 12/15, which is 8/10 or 4/5. And if we take the short leg to the long leg, 6/8 and then 9/12, they both reduce to 0.75, which is 3/4. So, mathematicians have given names to the ratios of the sides related to the acute angle. So rather than solving for each one of these using the proportions and writing them out each time, you now can substitute with a name. So here's our triangle, and we are now going to name one of those proportions, which was the length of the leg opposite the acute angle. So we're talking about the acute angle X, the leg opposite is YZ, being divided by the hypotenuse, and we call that the sine. The length of the adjacent leg to angle X would be XZ, and that would be in proportion to the hypotenuse, and that is the cosine. And then we have the tangent, which is the length of the leg opposite the angle, YZ, in proportion to the length of the leg adjacent, which is XZ, and that is the tan. Now, when we're using these proportions, tan, cosine, and tangent, we will rarely be talking about the 90-degree angle. We will almost always be talking about the acute angles, either X or Y, and the proportions that are derived from them. So with angle X, the adjacent side to angle X is the side next to it that is not the hypotenuse. So you will not use a hypotenuse as an adjacent leg. So the adjacent side to angle X is XZ. The opposite side is YZ, and the hypotenuse is XY. The same goes for angle Y. The adjacent side would be YZ, the opposite side would be XZ. So here are our basic trig ratios. The generalized right triangle ABC has sides with lengths of A, B, and C. You'll remember this picture from the P theorem. The side opposite the large letter for the angle will be a small letter. So the side opposite angle A is small a, the side opposite angle B is small b, and the side opposite angle C is small c, where each lowercase side length is opposite its corresponding vertex. So now let's take a look at our ratios, and this is what you need to have in your notes. You should have a drawing of this triangle, and then you can shorten and abbreviate the names of the ratios. So sine now becomes SIN. Sine angle A equals opposite over hypotenuse, which would be the sine A, which would be the ratio A over C. So that's opposite over hypotenuse. Cosine angle A would be adjacent, which is B, over hypotenuse, which is C. And the tan of angle A would be the opposite, A, over the adjacent, B. And that's how we get these ratios. So you can remember them by using opposite over hypotenuse, or you can remember them using A over C with your drawing. Let's take a look at example 1. We have a triangle ABC. We have values for 2 of the sides. We do not have a value for the third side. It asks us to state the exact values and decimal approximations of the sine, cosine, and tangent of angle A. When they say state the exact values, they are talking about a fraction. If they say decimal approximation, it will be the decimal that is derived from that fraction, and most likely will be approximate. When you're doing the decimal, you want to go out 4 spaces unless the decimal is a finite decimal, and in that case, example, say it's 0.875, you do not have to add a 0 on the end. So let's look at sine of angle A, and angle A is right here. The sine is opposite over hypotenuse, so that's 5 over 9. 5/9 equals 0.5556. Now to solve the other two ratios, we have to have AC. So we'll solve for AC by using the P theorem. And AC squared plus 5 squared equals 9 squared. AC squared equals 81 minus 25, which is 56. So the square root of AC squared would be the square root of 56, and that equals 2 square root of 14. You have to use the square root form here. You cannot use the decimal. It will not work. Now let's solve for cosine of angle A. And we have angle A here. Cosine is adjacent over hypotenuse. So we know now what the adjacent side is going to be. And let me draw it in here. And the adjacent side will be 2 square root of 14. So we'll have 2 square root of 14 over the hypotenuse, which is 9, and that's approximately 0.8315. Now we can do the tangent of angle A. Tan angle A is opposite over hypotenuse, so that's 5 over 2 square root of 14. We want to normalize our rationalize our square root. So once doing that, we'll have 5 square root of 14 over 28, and that cannot be reduced, and that will equal 0.6682. For 12.1a, you will be doing numbers 1 through 12, and let's take a look at a few examples. So homework problem number 2 says state the exact value of each trig ratio for the given angle in the right triangle. So let's first state what our ratios are. Sine will be opposite over hypotenuse. And the opposite of sine B, or angle B, will be 4, and the hypotenuse is 5. Cosine will be adjacent over hypotenuse, and that will be 3 over 5. And then our tan will be opposite over adjacent. So tan of angle B will be opposite 4 over adjacent, which is 3. And that's very simple. Where it gets complicated is when you don't have one of the side lengths. Let's take a look at problem 4. We have 3 side lengths. One of them is a square root. So we're going to go ahead and solve for the sine of angle E, and that will be opposite over hypotenuse. So the opposite will be 6. The hypotenuse will be, and bear with me while I do this, square root of 61. Now we want to rationalize, so we'll multiply by 1, and we end up with 6 square root of 61 over 61. Now we'll do cosine of angle E, which is adjacent over hypotenuse, so that will be 5 over the square root of 61. And once again, we'll go ahead and multiply by 1, and our answer is 5 square root of 61 over 61. And then we'll do our tan angle E. That will be opposite, which is 6, over adjacent, which is 5. And there you have it. Homework problem number 8 asks us to state a decimal approximation to 4 decimal places of each trig ratio. Now the last two problems said to state exact values. So we're using fractions in our answers, but this asks for decimal approximation. So we'll be doing decimals. And sorry, I needed to add our triangle. And with this triangle, you can see that we're missing one side. So one of the things I can see is that we can do our tan angle B, which is opposite over adjacent, which is 30 over 16, and that will equal 1.875. So let's go up to sine B. What we need to do is use our P formula to solve for this side length. And we'll go ahead and find my notes. We'll have 30 squared plus 16 squared equals AB squared. 30 squared plus 16 squared is 1156. That's 902.56 equals AB squared. And we'll take the square root of both sides. AB will equal 34. So now we will have our side length of 34. And we can continue on with our problem. So sine angle B will be opposite, which is 30, over hypotenuse, which is 34. And 30 34ths will become 0.8824. And now we'll solve for cosine B. Sorry, there's numbers in there. They don't belong there. Cosine is adjacent, which is 16, over the hypotenuse of 34. And that will be 0.4706. So when solving for the decimal, you'll find your fraction, and then you can go ahead and use your calculator for your decimal. You will see that the first two have an approximation sign, but the last one does not. That is because the last one was a finite decimal. it was actually 1.875 without any numbers after it. And that will be it for the demo for the homework. If you have any questions, please be sure to contact me, and we'll move on to lesson 12.1b, more trig ratios.